would you say that kids do well on this test, that were chapter 9 test?
I don't remember, honestly. All right. I am so going to talk about them. If I get too caught up in the lesson, don't let me forget that I want to say mean things about the people who chose not to be in this class and made me have to record it. All right. Yeah, you know I'm talking about you. Now look, now they made my whole thing freeze, stupid people. Okay. So we talked about the alternating remainder or the alternating series error. Okay, so we have one kind of an error. Today we talk about, well, can you do an error type thing like that if it's not alternating? That's what today is about. Okay, so annoying. It's all their fault. I had it going. Okay. This is called Lagrange form of remainder. Sometimes it's called Lagrange error bound. Sometimes it's called Taylor's theorem. You're never going to not know what they're talking about because they're going to mention error. And so then you'll ask yourself, oh, they said error. Is it the alternating or is it not the alternating? Okay, those are the only two kinds of error we do. All right, so when a Taylor polynomial, so when you have a finite polynomial, right, when a Taylor polynomial is used to approximate a function, we need a way to see how accurately the polynomial approximates the function. So my f of x, the actual function, right, is equivalent to whatever our polynomial approximate value is, plus the rest of the terms that we're not using, right? So if we just use that first polynomial to approximate it, then the rest of it is basically the remainder. That's how much I'm not using in my approximation. With me? So that means that r, the remainder, we call it r sub n. So if I use 3 terms to approximate, then I would say the remainder after 3 terms. If I use 5 terms to approximate, I would say the remainder after 5 terms. Okay? So the remainder is basically solve that equation. We could also call it f of x minus whatever our polynomial approximation is, right? And the only reason I'm showing you this notation is because sometimes they use the word error. Sometimes they use this remainder notation, and sometimes they use this notation of saying f of x minus p of x. When you see any of those things, that means error, use that Lagrange thing that we talked about on the very last day of new material. Okay? Any of those notations means use this error method. Got the idea? Okay. So what's going on? Oh my goodness, a bunch of blah, blah, blah stuff. Essentially, I just wanted to show you that it's also called Taylor's theorem. So here's the idea. This is the polynomial. This is the generic form of the polynomial, right? You got this written, right? So you don't have to write this, okay? This is the generic form of the polynomial. And then we're saying whatever the rest of the terms are, we're just calling it that r sub n, okay? So there's my polynomial. This is our formula, the one you have to know, that represents the rest of the terms. Okay? This is what you have to know. When you see this error or this Taylor theorem or whatever, that's what you want to write down. You'll notice in every single problem I do, I'll start by writing down the setup. Because so often, I can't tell you how many times I see people, they know the setup, and they get the point, and then they make the mistake. But at least that way you got one of the 2 points. Whereas if you don't write the setup and you just go straight to the mistake, you got squat. Okay? So there's my setup. So let's talk about what this means. Is it the same as the alternating series where you just look at the next omitted term? Because let's look. The n plus 1 derivative, isn't that the next term? Right? If the polynomial ended with the nth derivative, isn't the next term the n plus 1 derivative? And on the polynomial, you know, if it ends with the n term, it's over n factorial. This one's over n plus 1. So far, it's looking like the next omitted term, isn't it? You know how you have your x minus c? This is the x minus c to the n. So what's different? How is this not the next omitted term? What the heck is that? Z? We haven't talked about z before, have we? So that's what makes this a little different than just, it's very close, but that's what makes this different than just the next omitted term. All right, here's how it works. When applying Taylor's formula, we would not expect to be able to find the exact value of z. In other words, a lot of times you don't know what that exact value is of that next derivative term. You with me? You don't know what that exact value is. So rather, we're going to attempt to find a maximum value for the n plus 1 derivative. So when we say the n plus 1 derivative at z, that's not the exact value of the n plus 1 derivative. That's the maximum that it could be. It's kind of like we're estimating high. So we're going to estimate our error high. You with me? Okay. So again, the f of x minus p, that's just the notation for remainder. I automatically say, okay, remainder or error is less than or equal to, and I present that notation. And I present it in absolute value because we don't care about positive or negative, right? When we're talking about a remainder, because in the end we're going to add it to one side and subtract it from the other side. Okay. So how do I find this maximum? All right, it's similar to alternating series in that you're looking for the next omitted term. However, Lagrange forces you to consider the maximum value of the next derivative. It's going to be very rare that you know the exact value of the next derivative. Okay, so let's see how it works. Let f be a function with 5 derivatives on the interval from 2 to 3. Assume that, what is that notation? The fifth derivative. So assume that the absolute value of the fifth derivative is less than 0.2. Didn't they just tell me the maximum value of the fifth derivative? Sometimes when you get lucky, they hand you the maximum value on a silver platter. Sometimes you have to figure it out yourself, but sometimes when they say this, they're like, look, here's the maximum value of the fifth derivative. Now go plug it into the formula like you did in Algebra 1. You ready? Okay, so they give me the maximum fifth derivative. I know I'm on the interval from 2 to 3. I want, it says, and that the fourth degree Taylor polynomial for f centered at c equals 2 is used to estimate f of 3. Okay, how accurate is the approximation? What are they asking me to find? Do they want me to find the actual approximation, or do they want me to find the error in the approximation? Yeah, if they say how accurate is it, aren't they saying just what's the error? So that's another word to say what's the error. All right, so immediately I think about my, can you write it without looking? Immediately I think about my error formula. Say something about how the error is less than or equal to that absolute value. That's my formula. I'm just writing it there so we can have it. You've got it on your page up higher, I think, right? So that's my generic. So let's apply this to the problem. Okay, let's apply this to the problem. They said to use the fourth degree Taylor polynomial, so my notation will be r sub 4. So this is the remainder or the error after 4 terms. Okay, just for notation, it has to be less than or equal to what derivative? The what derivative? The fifth derivative, right? Because my polynomial was 4 terms, so I'm looking at the next term, which would be the fifth derivative over 5 factorial. Now, let me stop for just a minute. First of all, still cussing Miss Beckles with my pointer. Is everybody okay with my fifth derivative at z notation? You okay with the 5 factorial? What the heck is this? I thought it was x minus 2 to the fifth. Well, what is x? When they say f of 3, aren't they telling me x is 3? Do you see that? Everybody okay? John, you're making a face, you all right?
Can you explain that? Oh, no, I know.
You okay? So, what is the fifth derivative at z? That is the maximum. What is the maximum fifth derivative? Oh, they handed it to me up there in the problem. What is it? It's 0.2. So in place of fifth derivative at z, I'm going to put in 0.2. if I put in 0.2 and I multiply it by 1 to the 5th and I divide by 5 factorial, isn't that what I get? Everybody with me? For the sake of time, do you want to let me just do the calculator work up here? Because they said to approximate it to 4 decimal places, so you would put it in your calculator to get it, okay? But I'm telling you, I did that, and I got 0.00166. When I put that in my calculator, I got 0.00166. So I'm saying that the error based on a fourth degree polynomial is less than or equal to 0.00166. And you always want to use that notation. Don't say the error is this number. No, the error is less than or equal to that number.
So you always are finding the remainder for the smaller term, which is the smaller degree. You're trying to find remainder or the R sub 4 instead of R sub 5.
Yeah. So this is saying the notation here. This is saying the remainder. The way you would read the remainder after the 4th degree is represented by the 5th degree.
Okay.
Yeah. So yes is the answer to your question.
I'm confused as to how you got it. Why is there another inequality right there with the 0.2 over 120?
Oh, I just did some simplifying. Since that said the remainder is less than this, that means it's less than, I just did some simplifying. I just kept my instead of saying equals, I kept my notation less than or equal, less than or equal.
Okay, so you already simplified the 3 minus 2 to the 5th.
Yeah. If I have my handy dandy pointer, I simplified that to be 1, so all I really have is 0.2 over 5 factorial.
Okay,
It's just simplifying that absolute value.
Okay, yes, thank you.
Okay? Part B. Suppose that the polynomial, when I added up those 4 terms, suppose that it actually equaled 1.763. Remember how we did that on alternating? We would add them up. This says, use the answer to part A to find an interval in which f of 3 must lie. Do it just like we did alternating. Don't we say, okay, the actual value is between, what do I have on this side? The polynomial estimate, what? Minus the error, and the polynomial estimate plus the error. Isn't that how we set up when we did alternating error? So we're setting up the interval the exact same way. We're just finding the error a little bit differently. Why am I doing it differently than the alternating? Because number 1, they told me to. And number 2, I don't know that this is alternating. And then if I wanted to simplify, basically I'm saying that f of 3 is between 1.761 and 1.765. So it's very similar to the alternating, but it's not exactly the same. We're going to practice some more, but that's the general way we do it. Very similar. It's just that I have to always consider what's the maximum next derivative. Okay, so far? All right, look at my next one. Find the 5th degree Maclaurin polynomial, Maclaurin, for f of x equals sine x. Hey, we know that one, don't we? Can you write it without looking? The sine x. Okay, the 5th degree polynomial is, see if you can remember the sign. Is that the even or odd one? That's the odd one. What does it start with? X. Starts with x to the first. So can you write the sine one? If this were a free response, that would get you a point by knowing that sine one. If you don't remember it, you could always develop it, but who wants to do that, right? I mean, Monica, I know you like writing out the derivatives. You might want to, but nobody else wants to do that. You got it? What'd you write? X what? Minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Did you get it? Did you get that, Rania, all by your little self? Rania, come on, you're better than that. You're not Sarah or Evie. They're probably at home forgetting everything they knew about Taylor series. Okay. It said write the the fifth degree, check, then use your polynomial. I'm still on part A. Then use your polynomial to approximate the sine of 1.45. What do they want me to do? Don't they just want me to plug in 1.45 in my in for x? You want me to do that for you? All right, that comes out to be 0.9953. Y'all understand? We're just plugging it in the calculator, right? Just putting 1.45 in for x in each of those terms, right? And then it says, and use Taylor's theorem, that's the one we just learned, that Lagrange error, to find the maximum error for your approximation. Give 4 decimal places. All right, so this polynomial was based on how many terms? Well, I should say, based on what degree? 5th degree. So we would say r sub 5. That means the remainder or the error after 5 terms. So if it's based on a 5th degree, which derivative are we looking at in our error formula? The 6th. So can you write out the error formula for the 6th derivative for the 6th degree?
Why did you only go to x to the 5th?
Because it said they wanted a 5th degree Maclaurin polynomial.
Oh.
So even though it was only 3 terms, it was still 5th degree. Yeah. Everybody understand my notation? So I'm using the 6th degree. I always write at z because I don't know what z is. I'm going to put in a number in a minute for that maximum 6th derivative. To me, for these problems, the hardest part about them, assuming you know the formula, the hardest part about them is this. How do I know what the maximum of the 6th derivative is? On the last one, they gave it to me. Okay, how do I know what the maximum of the 6th derivative is? Well, what are all of my derivatives? I started with sine. Derivative is cosine. Doesn't it go back and forth, sine and cosine, I mean positive and negative, but wouldn't all the derivatives go back and forth? So I don't have to get to the actual 6th derivative to know it's either sine or cosine. Agreed? Well, think about sine or cosine. Sine or cosine ranges from where to where? -1 to 1. What we care about is the maximum. So whether my 6th derivative is sine or cosine, what would be the maximum value of that derivative? Wouldn't it be 1? So in place of the 6th derivative at z, we're going to put in a 1. Why? Because that's the maximum that 6th derivative could be. Got the idea? So sine and cosine are nice because the maximum is always 1. So I'm going to replace that circle with a 1. What do I put in place of x? Didn't they give me x up in the problem? Right? They gave me the 1.45. So they're always going to give you the x to put in. The only thing we're going to have to be kind of guessing at or speculating on is that next derivative maximum term. Everybody okay? And if I put that in my calculator, glad you asked, I get 0.0129. No. No. Tell her mom to come down here and sit for a few minutes. I'm kidding. At least Rania stayed this long. Good job, Rania. You're not like some people, Evie and Sarah. Thank you. Okay. Yeah, so like how I know that the 6th derivative is sine or cosine? Is that what you're asking me?
She's asking another 1.
Or why it's a 1. Okay. Well, think about the sine graph and the cosine graph. I mean, the sine graph starts here. The highest it goes is 1, and then it comes down to -1 and back, right?
Yeah.
So the highest the sine will ever be is 1, and the lowest the sine will ever be is -1. Same thing for cosine, right? The highest the cosine will ever be is 1. It comes down, comes back, goes down to -1, but the highest it's going to be is 1.
So that's just asking for the
Right, so for there, we don't need to know the exact 6th derivative. I just need to know what's the maximum value. So whether that 6th derivative was sine or cosine, I don't care. I know it's one of them, but the highest value it'll ever be is going to be 1.
Will it ever be like infinity?
No. There's always going to be a way to come up with a maximum. And basically what I'm doing is I'm showing you a couple different problems of how to come up with a maximum. So sometimes they give it to you. A lot of times they use sine and cosine because we always know the maximum is 1. So that's really handy. We're going to do another one that's not different again. Okay? So part B, use your answer to part A to find an interval. Well, I've got the polynomial approximation, right, that 0.9953, and I've got my error approximation. So can't I say that the actual value is between, what do? Don't I subtract on one side and add on the other side? Right? Isn't it going to be the 0.9953 minus that error, and then the 0.9953 plus the error? Right. Joanna, how come you made her ask me? Have I scared you over the past several years, or what?
She was asking me because you were talking.
Oh,
I just don't
I
know how to
gotcha.
explain it well.
I got you. Thought maybe this was one of those, I don't want to ask. So thought, Joanna, you're never scared of me. All right, and then if I simplify, just so you know, just because I know some of you won't settle unless you get it, it's going to be 0.9824 and 1.0082. Again, that'd all be calculator stuff.
So you wouldn't have to simplify to that.
You don't have to, no. But you're going to want to because of part C.
Okay.
Because part C says, could the sine of 1.45 equal 0.9777? No, why not? It's not in the interval. So when I said the sine of 1.45 was between those two, I was doing it based on my estimate with my fifth degree, right? But now it says, what is the actual value of sine of 1.45? How do I know what the actual value is? Yeah, I would just, on my calculator, I would do sine of 1.45. And if on my calculator I typed it in, I would get 0.9927. No. This is just for us to think about, but the next part would be, and so I was leading you there. I have seen this next part. How big is your actual error? So we said our error was less than, and then we said our error was in this range, or our actual value was in this range, right? But I didn't know what the exact error was. I knew the error was less than or equal to 0.0129. So how would I find the actual error? Isn't it going to be the value of the function right here minus our polynomial estimate? You see how that would tell me my actual error? Why are you smiling?
So for part A, we found the error for our error?
No. Part A, we found our error, we said our error is less than or equal to 0.0129. We didn't know exactly what the error was. We just knew that it was less than that. We weren't off by more than that. And now I'm saying, how much were we really off by? When we did the real value compared to the polynomial value, how much were we really off by? So if I take my function value, which is the 0.9927, and if I subtract out my polynomial estimate, which was the 0.9953, I was actually off by 0.0026. That's how much I was truly off by using those terms for my estimate. So was my error approximation up there accurate? Was the real error actually less than or equal to 0.0129? Is that less than 0.0129? Yes. So this is just showing that my error estimate was accurate in that it had to be less than that number. Okay? One more. You got it in you, okay? I feel it. You got it in you. Anybody want to say anything bad about those people that are not here? Maya, did me say out loud what you just said? I don't talk like that. My grandma always said, if you don't have something nice to say, don't say anything at all. I have disappointed her many times. Okay, write the fourth degree Maclaurin polynomial for E. Oh, yay, we get another chance to show what we know. Oh, come on, you know. E, is that the one that's even or odd? E is everything. It has all of them, right? Is it alternating? No. So e starts with what? 1 plus what? X plus x squared over, keep going, plus x to the third over, plus x to the fourth over. They want the fourth degree Maclaurin polynomial. Hey, should I remember to put dot, dot, dot? No, why not? They said what word? Polynomial. That means cut it off. No dot, dot, dots. Okay? Then use your polynomial to approximate e. And e is the same as e to the first, correct? Would you agree? So if I'm approximating e to the first, what are they telling me to let x equal? I can't hear you. 1, right? By saying approximating e, that's the same as e to the first. So they're saying, hey, let x equal 1. If they had said approximate e squared, then they'd be telling me, oh, x is 2. Okay? Joanna, you okay?
So why is x 1?
Well, when they said we're going to approximate e, that's like e to the first, right?
Okay.
But my function was e to the x.
Mm-hmm.
So when they said approximate e, aren't they putting in a 1 in place of x? Instead of e to the x, they're saying e to the first.
Okay.
So they're just putting a 1 in place of x.
Okay.
Okay? So we are going to approximate e using this polynomial. Let's see, then use your polynomial to approximate e. Okay, so what does that mean? Plug in a 1 everywhere you see an x. What do we get if we plug in a 1 everywhere we see an x? Don't we get 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial plus 1 to the 4th over 4 factorial? Everybody see what I'm doing? I'm just plugging in 1. So I'm saying the value of e to the first is approximately this polynomial, which comes out to be 2.7083. Everybody understand what I did to get that? Okay? So they said, use your polynomial to approximate e. Check, I just did that. And what's the last thing they tell me to do? Find what? A Lagrange error bound for the maximum error when x is less than or equal to 1. That's weird. We'll come back to that in a minute. All right. So I want, what would have been my notation? R sub what?
4.
R sub 4, because that's how many terms you used in your polynomial. But now when I set up my formula, what derivative am I going to use? The fifth. So set up your formula for the error. See if you can write it down without looking. Absolute value. You see what I mean? How I'm writing down that formula every time with the correct derivative term. And when we first write it, we just say the fifth derivative at z, right? We'll figure out what that is in a minute. Okay.
Ours doesn't say Maclaurin.
Pardon me?
Ours doesn't say Maclaurin.
What does it say?
It says Taylor.
But does it say where it is centered?
No.
Huh. Okay, well, it's Maclaurin. Because if they didn't tell you Maclaurin, they would have to tell you where it's centered. Right? Everybody okay? So, in order to come up with this value, what is it I need to find? I need to find the maximum fifth derivative. Okay, well, let's think about this. If f of x is e to the x, what's first derivative? E to the x. Second? Third? Fourth? 100th? So I know the derivative is e to the x, right? I need to figure out what's the maximum value, because think about the e to the x curve. It could go up forever, right? So I need to think about what's the maximum fifth derivative, but notice they said that the absolute value of x is less than or equal to 1. That means x is what? Between, so I'm only looking from when x is between -1 and 1. So what's going to be the highest value of e to the x between -1 and 1? Is it going to be over at -1? What's e to the -1? 1 over e. Or is it going to be over at +1? What's e to the +1? So isn't the highest value of e to the x, if you're only looking from -1, isn't it going to be over there at 1? So the highest value of the derivative, which is e to the x, is when x equals 1. Isn't that just e? So do you see that my maximum fifth derivative is just e? So a lot of times they'll use the e function because we know that the derivative, no matter which derivative it is e to the x. And then somehow they'll tell you, oh, only look at this interval. We good? So in place of that fifth derivative, I'm going to put in e. Remember, we already knew x was 1, right? So e over 120, I mean, everybody just knows that off the top of your head. It's 0.0226. I mean, people that aren't here probably don't know, but you all know. And then what does it say to do? Find an interval such that e is between a and b. Well, we know, let's see, my error is less than or equal to 0.0226. My polynomial estimate was that 2.7083. So aren't I going to do a minus and then a plus? Right? I didn't write the minus and plus on mine. I just went to the final answer. Oh, man, I lied to you. Is it still a lie if it was unintentional? It is? Okay, then I lied to you. But isn't there something about, like, you know, the motive of your heart or something? What? Yeah, there you go. I was wrong because there's one more example. Oh, we got it. Here we go. Ready? Write, this is an easier one. Write the third degree Taylor polynomial about x equals 2. Hey, they give me all the stuff I need. You ready? So I'm going to say third degree polynomial is, what's f of 2? Look at, what is it? 6. And then how do I get the next term? Isn't it the first derivative times x minus 2 since it's centered at 2? You with me? I'm using the formula. And then I need the, what's the second derivative? -7. Wouldn't it be x minus 2 squared over 2 factorial? Everybody see what I'm doing? I'm just using these to plug in. And then the last one, 8, x minus 2 cubed over 3 factorial. Use it to approximate f of 2.3. So what do they want me to do? Plug in 2.3. Well, luckily for you, I did the math. If you plug in 2.3, you get 6.921. That's all just a calculator thing, right? Everybody okay? All right. Ready for part B? The fourth derivative satisfies the inequality. What did they do? They gave us the maximum. Thank you, Lord. Right? They gave us the maximum. We're only looking at the closed interval from 2 to 2.3. It says use Lagrange error bound on the approximation found in part A to find the interval. So then wants to go all the way to the interval. So let's set up our error notation. So if this is based on the third degree polynomial, we would say r sub 3. Can you set up the formula for the error? Right? Set up your absolute value. Which derivative are we using? Aren't we using the fourth derivative? Because it was a third degree polynomial. Don't forget it. This one was centered at 2, so you're going to have the x minus 2 to the fourth. Everybody doing okay? Luckily, they gave us the maximum. So what are we going to put in place of fourth derivative at z? We're going to put in a 9, and I've got my over 4 factorial. What am I putting in place of x? 2.3. So I'm filling in my fourth derivative. I'm filling in my 2.3. You want me to do the math for you again on that one? Just for you all. I'm not doing it for the ones that aren't here. So I would get 0.003. You guys that aren't here, that is not for you. Let's see, did I do everything? Oh, they want me to go on to the interval. Well, look, I've got my polynomial approximation up above, right? And on part B, I've got my error. So can we just automatically sit up and say, all right, f of 2.3 is between, and you all know what we would do, right? You know, we would add and subtract. So if you want the numbers, 6.918 and 6.924. Everybody's okay with where that's coming from, right? Subtracting on the one side, adding to the other side.
The part you put in the middle is always the function of this.
Yeah, that's like what we're saying. The actual value is somewhere in this range. Yeah. Could f of 2.3 be 6.922? Yes. How do you know that? Because it's in the interval. I feel like, I know I rushed at the end, I'm sorry, but I feel like we got through enough examples that you could start to see the repetition, and that the interval part is very similar. The only difference is coming up with that maximum derivative. Is everybody okay? We good? Hey, I'll tell you right now, the homework, it's pretty long because it's kind of a review in and of itself. It has a lot of the different things. It's not just this error stuff, okay? Yay, thank you for coming, everybody who came. I'm not talking to you people that aren't here. See you.